So finally, the fourth part of interpreting NMR spectra, it's the splitting patterns. This is probably the more challenging of the four, but once we have this down, we'll be able to solve NMR problems. And finally, the last important aspect of NMR spectroscopy is looking at the shape of the signals. This is also called multiplicity or the splitting pattern. And the splitting pattern can be as simple as a singlet, meaning a single peak, a doublet, a triplet, a quartet, a quintet, a sextet, a septet, and sometimes when it's unclear exactly how many are in the signal, you might call it a multiplet. Multiplicity results in the magnetic effects that protons have on each other. So if you think about HA and HB in the sample molecule here, since the protons can align either with or against the external magnetic field, there will be two different magnetic environments for HA, one up, one down, and so that's going to give us a doublet. Consider an example where you have two protons that are on a carbon next door to the one we're observing. Here are the three possible environments for HA. Both HB protons can be against, both HB protons can be with, and we can have one with, one against in two different patterns. And so what we'll see here is a triplet where the center signal is bigger because there's two possible scenarios for that configuration. Now, if you're thinking about a scenario where a proton HA is split by three equivalent protons, then again, we can have all three with, we can have all three against. We can have two up and one down, or we can have two down and one up in three different arrangements. Therefore, we're going to get a quartet, and the quartet is going to have the two peaks in the center larger and equal, and the two peaks on the side smaller and equal. By analyzing the splitting pattern of a signal in a proton NMR, you can determine the number of equivalent protons that are on the next door neighbor carbon. And the way that we can do that is if we have some n, which is the number of protons, then our n plus 1 is going to be what the peak shape is. So there are three key rules for splitting. Equivalent protons cannot split one another because they resonate together. To split each other, protons must be within 2 or 3 bond distance. And finally, the n plus 1 rule only applies to protons that are all equivalent. For example, splitting is observed between HA and HB in the two cases on the left. However, splitting is not observed in the molecule on the right between HA and HB because they are too far away from each other. The splitting pattern observed for this proton is going to be much more complex than a simple triplet because the proton that's on the carbon with the oxygen is different than the proton that's on the double bond. Those two non-equivalent protons are going to split the red proton differently. And so we'll talk a little bit more about this complex splitting in just a few slides. The other thing I want to mention here is J coupling. So the degree to which a neighboring proton will couple its neighbor is called the coupling constant, or J coupling, or the J value. The J value is the distance between the peaks of a splitting pattern. So it's the distance between this peak and this peak, which is the same as this distance and the same as this distance. So if you're looking at the quartet, HA gives the quartet, and HB gives the triplet. So the distance between these four peaks, here, here, and here, and the distance between these three peaks, here and here, is the same. So they have the same J value, which means that they are coupled to each other, or it means that they are on carbons next to each other. And so when you have the J value that's equal to each other, then that means that they have the same coupling constant, and that means that they are coupled to each other. Sometimes recognizable splitting patterns happen in your spectra. For example, if you see this, so we have integration now of 2H quartet right next to a 3H triplet, that pattern means you have an ethyl group. Of course, the J value has to be the same. Down here, this is not an ethyl group because the J value is different, and so these are not connected to each other. If you see this very tall singlet that has an integration of 9, then that's very typically going to be a tert-butyl group. So we have 9 hydrogens, and there's no hydrogens on the next door neighbor carbon. So it's a singlet, and it's integrated for 9. If you have a 1 hydrogen multiplet or septet right next to a 6H doublet, then that tells you that you have an isopropyl group. So the way I interpret this is I say, okay, so I have 6 hydrogens that are on a carbon next to one with doublet, -1, 1, next to one with 1 hydrogen. And I have 1 hydrogen that's on a carbon next to, this is 7, so we subtract 1, because remember it's n+1 in the signal. So we have a septet, so that would mean 6. So that means I have 1 hydrogen on a carbon next to one with 6. And so you can see how that works out. Complex splitting patterns definitely happen when you have 2 different kinds of protons, like 1 on each side, for example. So in the molecule below, HB is split into a quartet by HA, but it's split into a triplet by HC. So there's 3 different ways that we can have this happen. If the J value for AB is much greater than BC, we'll see a quartet of triplets. If, however, the J value for BC is much greater than AB, then the signal will appear as a triplet of quartets. But more typically what happens, the J value for BC is very similar to the J value for AB, and what that gives you is kind of a mixture of quartet and triplet, and you kind of get like this multiplet that's very confusing, but that tells you that there's protons on both sides that are splitting it a little differently. Now, this is just comparing 2 different size spectrometers, a 60 megahertz on the left and a 300 megahertz on the right. And so what happens is the higher field strength instrument on the right will give better resolution between the peaks because the coupling constant is a smaller percentage of the overall hertz available. And so I told you earlier, with the stronger magnetic field of the instrument, you're going to get much better peak resolution. And then I just wanted to share with you too that sometimes protons are not split. In this ethanol spectrum, we have a triplet down here about 1.25. That's a 3 proton triplet. And then we have a 2 proton quartet, and that's our ethyl group. And then right in the center, we have at about 2.25, a singlet, which represents the hydrogen that's on the oxygen. There you have it, multiplicity. Now you can solve NMR problems. There'll be one more video to give you a couple examples. For NMR, the most important thing to do is practice, practice, practice.